this video we move to the number 7 and 8 together to talking about the integral within calculus. Actually, it's, in calculus, if we look back from the mathematical, the structure is we starting from the definition of a function, and to understand the functions, they have the range and they have the domain, and also in the middle they have these rules, or we can use the earlier knowledge is that's the transformation rule. And the second is we did some this discussion about the limit of a function. So when we come to this infinity to the there's positive or negative, then that's will bring in this new type of the calculation within the calculus. And the third key message is key concept is the derivative. So we have used that to make this gradient ascent those method. In the later the challenge topic, we will make this inverse method is called this gradient descent method that can try to find the global those edging or the boundary value, either is a maximum, global maximum or global minimum. And from this video, we will discuss about another key concept in calculus is the integral. So integral in a simply way is the inverse operation to the derivative. So that is a very simple idea. So if you know how to do this derivative, then just make that vice versa, then that is the integral. And then we will use this integral, the knowledge to calculate the probability density and make that as a function. So let's see that, and from the book, is starting from this indefinite integral, or we call that is antiderivative. So from this word, it's very clear is the integral is the inverse operation of derivative. Then it's from the definition is talking about we have a function fx, is another function is capital Fx. And this derivative of this capital Fs or big Fx is small fx. So that means the integral of function is another function whose derivative is the original function. So mathematically, it's written as the big F with this integral, this symbol, and then fx dx. So d is, we can see that is the derivative means. And the definite integral is that means that you have the range from the lower to the higher. So if we say here is the below and above this integral symbol, you have the starting and the ending range. Then that code is definite integral. So you may already familiar this if you learned from college or university. For those mathematical part, and in the short, the simpler way, we can put that written as big FB minus big FA. So then in the those this kind of the ways we can try to implement that from the Python. So also we have our class called the integral within CPy. Similarly, is like is what we did is we have this derivative class within SymPy. Now, just SymPy already provide our ready this class that we can use. So we don't need to create our program. So let's practice this from the Python's terminal. So now let's make those import is from SymPy. Now we import a symbol. So that is naturally we should define certain the variables as a symbol. Then we import is integral. So just ensure those are the capital letters in the beginning. Then also, if we see here, it's better whenever you see you are using the multiple symbols. Try to import these symbols. Then we can use the known way. So x, comma k. We can use symbols, not a symbol. Now it's just within one pair of the single quotes. We can put x dot comma k. Then one line we can define multiple symbol. Then what we can do is integral. We have an expression or function, so k times x, and respect to x to do this integral. Then we will have this integral kx. So with your this college mathematical knowledge, it should be the half times kx square. So let's do the this calculate. So if we see we put this I equal to this integral k times x. Then if I do this I dot, then I got this result. So this result is from mathematical, it's very direct. And then that is the infinity, indefinite, the integral, because we didn't provide any the range or scope. If you want to do this definite, the integral, you will use this so-called this tuple like. Then this I put this I2. It's go integral k times x, and then with this tuple, I have our variable and give our the lower and upper range. So that means it's like we have this result, and first we replace x with 2 and minus another calculation, replace x with 0. So with 0, then this is 0. So if 2 is here is 2 times 2, divided 2 is 2. So it should be the 2k. So let's see. So I2 dot is 2k. So that is the easier way. So for you with this ready or built-in integral, the class or integral the function. So and that in the written, so that should be like this way. So maybe so let me see is if I from SymPy import pprint. So how I can print pprint I and I2. So what's that? Oh, so it's not allow us. Oh, you can see here. So it's not looks quite nice, but this is the integral. The symbol, so looks like they have this curve as well, so that's quite interesting. And kx dx, so that is better than, I think it's better than this. Where is our kx dx? So it's this one. So this is written by this, and let's say I2. So now we have this scope here. So that looks like here. So even it's not easy to use this terminal to show all those special character, but this already give you some hints. This is the integral symbol. And now consider the region under the graph ABCD. So we can very easy to use the plotting to show the concept of the integral, because integral is actually is like to calculate the one level up above the dimensions. So for this this one, so 0 is fx equal to x is from x to from 0 to 5 is this line, or this the part of the line. So and then it's ABCD. So A not A, B, C, D, it's A, B, D, E is the integral between 2 and 4. So that is the thing is we can try this. So first is x is equal, we already have x, I think. So then let's directly use this line. So see the big L is integral x. So that is our x is our expression. Then x 2 to 4. So we have this L. We can print L. So now you can see it has this boundary 2 to 4. So let's do this dot. So I got 6. So that is the integrals calculation. Understanding that the definite integral is the area enclosed by the function between the specific point on the xl is key for understanding probability calculation. So this integral actually is first we have our function. So d and e both are in our function. So it's this range. We have this the function result. Then the integral is the this area below this scope of the line, and then until till this 2xl. So this rectangle plus this triangle. So with this knowledge, we can understand the probability density. So what that means is normally that is like our density percentage based on certain distribution, or we call this standard this deviation. So that normally is like such kind of the curve. And what we want to understand is if the probability happened. So this probability mostly is happened around possible here is 6 or 6 to 7, and here is 13 or 14. Within that, and we want to understand is what's the probability happened between 11 and 12. And now we know is these are the this gray area is the probability, and the density means this divided by the whole this occurring the probability, and then this gray area or gray color area actually now through this function x, we know is just the integral of this function with this scope from 11 to 12. So we can use this this integral the way to show that, and the px is our probability this curve, and to calculate that is now we know is the probability density function we assumed earlier is this function. So px is this one. Then when we replace px with this, looks is quite this quite complex, but if we convert that to our this function is not so much complicated. So we already have a symbol and integral import. Let's just import those mathematical function, but we will use the syntactic function, not math, because math cannot handle the symbolic expressions. We discussed that. So we do this one and import this exp functions, square root function, and also this constant pi. So when we say pi is here is our this you can see that is our the expression. But if I put this mass pi, so from mass import pi, I think it's mass dot pi. Is mass is not defined. So it might say here now this pi is the value. So if I put this one is no. So I need to I think it's I need to again import this pi is because it's getting overwritten by the mass pi. Then is we have the necessary the library or class. Then is x is already defined. then we can make this a p. So let's use the small p, so easier. So px is this, so just the exp with this part, and times this, and we can use that divided by this one. So it's not easy, not complicated. So exp, when we have this exp, then is the minus is x minus 10, and with the square 2, and then divided by 2. So that is on this exp parts, and then divided the square root of 2 times pi. So it's quite easy. So it's just let's p print p. So it's like this way. So that is it's not so so good, but they put this the square root 2 to this square root 2 divided by 2. So that is actually square root 2 is under this line. So and e is with this one. So if we just make the normal print, then it's coming to this expression. So that is the advantage for this the perfect this print. So and then this will, what we will do is we directly is go to the I is the integral with p, and what we do is x with the range 11 and 12. So I is this one. So let's make the pretty print I. So you can see here we have this range with this integral symbol, and here is the px, and here is the dx. Then what we can do is we can starting to do this I dot. So this is the calculation, and when we do this evaluation of this function, then we can get this calculate. So we will do this and evaluate f. So it's 13500 something. So that is the possibility, probability of this gray area compared to the total distribution curve. So we create this integral object for the function, with p represent this probability density function that specifies we want to calculate the definite integral between 11 and 12 on the x-axis. So then it's evaluate using this EVLF function using this dot, and find the numerical value using this one. So the probability is about 14%. So strict speaking is that the density function assigned are non-zero probability to grade less than 0 or greater than this 20. So you can get that just have a look. And the probability density function has two specific special properties we should be aware. First is the function value for any x is always greater than 0, because this curve is above the x-axis, as the probability can't be less than 0. That's the probability. So that's again is the something is when you see only from this the algebra the mathematical way is definitely can be both positive, negative, or any value. But from some this practical way, because we are talking the probability now, it cannot be our negative number. So that's its first property. Second is the value of this definite the integral for this one. If we see is will be equal to 1, but if we just put our range is we are approaching to 1. So we can also put let's see here. So if I change this, so maybe let me. Now we can see it's just 14%. So let me see it's 400. is 100. Then we, if we do this, so you can see it's already quite almost 1. So if we see, so here is just 10 to 10. So that is the half. So this is the, what we can see is 50%. So that is the way is you can make your this probability to see. So if I see it's 40, 40, so that we are getting the higher. So already the 1%, 100. So if we put that negative infinity and this, we don't need to positive word. So here, then you need to import S, the capital S. Then you can practice this one. Then it's 1, and you can see here is even not the infinity, the number is just more than 40, negative 40, positive 40 is already approaching to 1. So that is the this probability is the character. So it's like our this standard the deviation. The curve, so it's very quickly is to approaching to the 100%. So that is the roughly the contents we have approaching. Now is finished this chapter. So in this chapter, you learned how to find the limit, derivative, integral of function, and you learned about this gradient ascent method for finding the maximum value, and we will later have this gradient descent method to find the minimum value of a function. And then this we also have using the applied integration principle to calculate the probability of continuous random variables. So we have already practiced quite a lot of the these calculus. Definitely, this is not the complete calculus the problems, but until now, I hope is we have introduced the key concept within the calculus, but which more important is we show you how to use Python to deal with those problems. So then this I hope to give you the enough confidence already is using Python you can deal with even such kind of deep level mathematics problems. So moving forward is we will have 4 the programming challenges. We will verify the continuity of the function. So that's the first and the next video. And then we will implement this this gradient ascent and to do this inverse one. So let's make that our the connection. And we will find the area between 2 curves. So now we will expand from what we learned in this integral. We discuss about 1 functions or 1 curve of this the area. And then this if you have 2 curves, these 2 curves have the area between them. So what that means? So simply speaking, it's just the integral 1 minus integral 2. So then you get this delta. So that is the between. Last but not least, the challenge is to find the length of the curve. So we know how to find the area. Now it's let's see if you have not irregular curve, how this certain length on this curve can be calculated. It's not the estimate, it's the calculate, because you are now have the calculus in your weapon, this library. So I hope it's that will be for the exciting the programming challenges looking forward. So see you in those videos then. Bye for now.